In this video, we are going to talk about the pH of salts. Now, remember, when you're talking about a salt in chemistry, we are talking about any ionic compound. And when you have a neutralization reaction, so remember, a neutralization reaction is a reaction between an acid and a base. So if you have a neutralization reaction between an acid and a base, you're generally going to produce water and a salt. And that salt is going to be the ionic compound. Now, when that happens, we can have different types of salts. So the salts can be acidic, basic, or neutral. So an acidic salt is going to have it consists of the conjugate base of a strong acid and the conjugate acid of a weak base. And so in solution, the conjugate base of that strong acid is not going to react with water at all because the strong acid completely dissociates, whereas the conjugate acid of the weak base will react with water because it does not completely dissociate. So a basic salt consists of the conjugate acid of a strong base and the conjugate base of a weak acid. Now, if you have a neutral salt, it is going to have the conjugate acids and bases from strong acids and bases. Now, when you're looking at the pH level of these different salts, the acidic salts will have a pH that is less than 7. Basic salts will have a pH that is greater than 7. And neutral salts will have a pH that is equal to 7. So let's look at an example. The first example we can look at is sodium chloride. So the first thing you need to do is find out where the cation and the anion come from. So we want to find out or determine where the cation and the anion come from. Remember, when we get these salts in solution, it is a result of a neutralization reaction. So generally, cations are going to come from bases. So in this case, we have sodium. And these bases are generally going to have hydroxide. So we're dealing with sodium hydroxide. So our cation is sodium, and I'm just going to pair that up with hydroxide. The anions come from the acids. And so I just like to add a proton to my anion. So I have chloride, which is a -1 charge, so I just have to add the 1 proton. So if you think about it, when we make this salt, it has to be the combination of sodium hydroxide reacting with hydrochloric acid to yield water and sodium chloride. So that's where that salt comes from. Now, I know that sodium hydroxide is a strong base, and I know that hydrochloric acid is a strong acid. So neither of these ions are going to react with water and exist in equilibrium. They can react with water in solution and they will completely dissociate. So since they're both from strong, we're going to get a neutral solution. So this means we have a neutral salt. And the pH is going to be equal to 7. Now, if we are, let's look at another example. So we can look at something like sodium cyanide. Now, sodium ion is going to come from a strong base, sodium hydroxide, and cyanide. If I add that proton, it becomes hydrocyanic acid, which is a weak acid. So, since I have a strong base and a weak acid, this is going to be a basic solution, which will provide a basic salt. Now we can calculate the pH of these different salt solutions if we have the concentration. So for an example, we can calculate the pH of a 0.250 molar sodium cyanide solution. So sodium hydroxide is a strong base, so I do not have to look up the Kb value for that. Cyanide comes from a weak acid, so I'm gonna need to look up the Ka for that. So if I go to the reference tables, I can find that the pKa for hydrocyanic acid is 9.21. Now I want to be very clear about this. We don't have hydrocyanic acid in solution. What we have is cyanide. And when cyanide is around water, it is not going to react into something that will completely dissociate because it's going to react to form hydrocyanic acid plus hydroxide. Now, in contrast to that, we can write this over here. Sodium, when it is in water, is going to make sodium hydroxide plus acid. Now, this sodium hydroxide will not exist in equilibrium, so it will just dissociate. So it doesn't matter that that is in there because we'll only have ions in solution. Now, cyanide is weak. it's going to make that hydrocyanic acid, which does not completely dissociate, so we will exist in equilibrium. So I can set this up like all of my rice tables. I'm going to start off with a concentration of cyanide, 0.250. Remember, sodium cyanide is completely soluble, so the concentration of the sodium cyanide is going to be equal to the concentration of the cyanide because it is a 1-to-1 mole ratio. We do not have any concentration for water, and we do not start off with any of our hydrocyanic acid or our hydroxide. So as we move forward, the change is going to be minus x, and plus x. So at equilibrium, we're going to have 0.250 minus x, and x. Now this pKa is very small, very, very small. So what that tells me is that I can use the assumption and I don't have to consider this x. Now, this is where I see a lot of mistakes. Cyanide is not behaving as an acid. It is behaving as a base. So I cannot use the pKa for this, but you'll notice the reverse process is Ka. So I can calculate Ka, or I can calculate Kb from Ka. And this is important. If you have cyanide and you want to try to find Kb for cyanide, you're not going to find it. Generally, only the Ka and Kb values are given for charge neutral species, or if it's a polyprotic acid, for the acids as you take off the protons. You're not going to find the pKb of a conjugate base like cyanide. So I can calculate Kb from Ka, and remember Ka plus Kb is equal to 14. So Kb is going to be equal to 14 minus 9.21, which is going to be equal to 4.79. So from there, I can calculate my, sorry, this should say P. My pKb, if I have my pKb, I can then calculate my Kb. So Kb is going to be equal to 10 to the negative pKb, which is equal to 10 to the negative 4.79. So if I calculate that out, I get 1.6 times 10 to the negative 5. Now, remember, this looks like all of our acid-base reactions in water. So I can use X is equal to the concentration of hydroxide, which is equal to the square root of Kb times the initial concentration of my cyanide. So when I plug that in, I'm going to get 1.6 times 10 to the negative 5, and I'm going to multiply that by 0.25. And I can take the square root of that. When I do that, I get 0.0020 molar. From here, since I have the concentration of hydroxide, I can calculate the pOH. And I can do that by getting the negative log of the 0.0020, which gives me 2.69. Now, at this point, you need to be careful. We've already established that this is a basic salt. 2.69 is not a basic pH. It is a basic pOH. So I can solve for my pH by subtracting it from 14. And I get a pH level of 11.31. And that pH level makes sense because it is a basic pH. We can look at another example, which is ammonium chloride. So, determine whether ammonium chloride is basic, acidic, or neutral, and calculate the pH of a 0.25 molar ammonium chloride solution. I would like you to try this problem on your own. If you have any questions, you can let me know.